Hello everyone, myself Anima Ghosh, Associate Professor, presently working in SR University, Warangal, Telangana. Today we came back with a lecture on crystal defects. In this lecture we will be discussing the classification and application. Basically in material science, we often begin by studying ideal crystal structure, perfect periodic arrangement of atoms extending infinitely in space. However, in reality, no crystal is perfectly ordered. Every material contains imperfection or irregularity in atomic arrangement. These irregularities are known as crystal defects. At first glance, the defects may seem undesirable because they disturb regular structure of crystal. But very surprisingly, however, the defects play a crucial and often beneficial role in determining the physical properties of materials. The strength of steel, the conductivity of the semiconductor, the color of gemstones, and the efficiency of light emitting diodes or solar cell are strongly influenced by presence and control of crystal defects. So understanding crystal defect is essential because mechanical deformation in metal occurs due to dislocation. Electrical conductivity in semiconductors is controlled through impurity defects, that is called as doping. Optical properties such as luminescence and color arise from the defect state. Advanced material rely on defect engineering to enhance performance. So in this lecture we will be systematically explore the classification of crystal defects based on their dimensionality, and we will distinguish between intrinsic and extrinsic defects, understanding how defects form and analyze how they influence material properties. Finally, we will explore some real world application where control defects engineering leads to improve performance in semiconductor, alloy and optoelectronic devices. So we'll be focusing on understanding the types of crystal defect, point defect, line defect. So point defect, line defect, surface and volume defect. Classification defects into intrinsic and extrinsic categories. Explain the origin and formation of mechanism of different defects and effect of defects on, in particular, electrical, mechanical and optical properties of the material, and will be conclude with some real world applications. So first let us look what is the crystal defect. So a perfect crystal is ideal structure where atoms are arranged in a periodic and repeating pattern. However, in real material, the perfect crystal do not exist. Deviation from ideal arrangement of atoms are known as the crystal defect. So a defect or an imperfection is basically any deviation from the perfect arrangement of atoms observed in real crystals. This repeated variation of long range orders would be in crystal structure. So based on the defects, the crystals, these different types of defects are classified as four types: the point defects, line defect, planar defect and volume defect. So point defect is basically also called as zero dimensional defect. So basically that very small or teeny defect in a point zero dimension, that's called point defect. Line defect, or it is also known as dislocation. It uh, dimensionally it told as one dimensional defect. Planar defect, two, it dimensionally it is two dimensional effect, and volume defect, that is the three dimensional defect. So first will we discuss on the point defect. So point defects are lattice error at this at isolated lattice point. So they are imperfect point like region 1 or 2 atomic diameter in size, and hence referred as zero dimensional defect. The point defect can be divided into four types, like vacancy, or it is also called as Schottky defect, interstitial or Frankel defects, impurities, and electronic defects. So let's come that what about point vacancies. Vacancy generally means the absence of atom from a site normally occupied in the lattice. So vacancies are produced during the solidification or solidification because of local disturbance or from thermal vibration of atom at high temperature. The concentration of vacancies in crystal depends on the temperature. Vacancies form in close packed metallic structure. So vacancy is the absence of an atom from a site normally occupied in the lattice. So here in this diagram we can see that here that atoms that with the round circle, those are closely packed, but here in this circle we can see that here has a empty space. So this part is called as the vacancy of this lattice. So vacancy are produced either solidification or thermal vibration. So the equilibrium concentration of vacancy on a metallic solid, that n represented as small n is equal to capital N, that is number of atoms, e to the power minus ev divided by kt. K is the Boltzmann constant, is the temperature, ev is the energy in balanced state. So the vacancy is the equilibrium concentration of vacancy on a metallic solid is given by in this picture. Next we will be discussing on the Schottky defect. So Schottky defect generally forms for ionic crystals. Is formed on for ionic crystal. So in case of ionic crystals, the formation of vacancy requires a local readjustment of charge, such as that charge neutrality is maintained in the crystal. Therefore, a pair of vacancies arises due to missing of one atom or an ion from the structure. Such pair of vacant site is called as Schottky defect. So a pair of one cation and one anion vacancy. The equilibrium concentration of Schottky defect in ionic crystal is defect in ionic crystal, that is defined by this equation. So here in the diagram we can see that we have given one solid circle and one anion and cation. So here we can see that after this solid line, there we can expect a line to complete the balance arrangement. So this absence of the absence of this uh, one cation and anion vacancy. Here it's called as, this is the Schottky defect, and this defect is generally observed in case of ionic crystal. So now coming to interstitial, that interstitial is an atom or on a lattice site. It here you can see that in this structure that here have the regular arrangement of the atom. So this atom basically is in half of this lower to these two atoms, same here. So this two is called as, that an interstitial is an off lattice atom which may be a we can consider as a foreign atom or a regular atom. So this interstitial is an atom or a non-lattice site as shown in this figure by, I have marked here by the red mark, and this arises when an atom occupies a position in the lattice that normally vacant in the perfect lattice. So now we will be discussing on the last one, that Frankel defects. So it is found in the ionic crystals. So it is an ion displacement from the lattice site into the interstitial site. A Frankel details is the combination or combined of one cation vacancy and one cation vacancy and one cation interstitial defect. So the equilibrium equation for this is written in this way, and atoms are uh, bigger in size, and they do not in a void space. We can see here that here arrangement is one bigger, one smaller, but we can see here that in this position there is two smaller. So this is basically the disbalanced. So a Frankel defect is the combined of one cation vacancy and one cation interstitial defect. This is observed, or this can see in the case of ionic crystals. So now we will be coming to the impurities. So an impurities is the substitution of regular atom with an atom that does not normally occupy the site. The impurities can occupy two different sites in lattice. An impurity atom may replace an atom of the parent lattice site. Such impurities are known as substantial impurity or substantial defect. Impurity may occupy in interstitial position, which is a non-atomic site. The impurities are known as the interstitial defect. So in this left side, this image we have seen there the substitutional and impurity atom, and here this position, this is the interstitial impurity. So now in the point defect, the last defect is the electronic defect. So error in charge distribution in solids are called as electronic defect. These defects are produced when the composition of an ionic crystal does not corresponds to the exact stoichiometry formula. The non-stoichiometry composition is caused by excess of metal ion. So let's say that in the zinc oxide, that ZnO, here zinc plus 2 and oxygen minus 2, this should be placed zinc plus 2 oxygen minus 2 in this way. But if you look at here in this part, then here this zinc plus 2 position is the excess. So this is as called as the electronic defect. So the non-stoichiometric composition is caused by excess of metal ions when the stoichiometric compound of ZnO, basically here we are talking about zinc oxide, is heated in presence of zinc vapor. A non-stoichiometric compound of zinc oxide is produced. Some of ionized atoms enter the lattice of zinc oxide and stay around as interstitial cations as shown in this figure. So since the crystal must be electrically neutral, the excess of cation must be balanced by the equal number of electrons. So this is found in the non-stoichiometry ionic crystals. So these all are here the vacancies, and then the interstitial, then impurities, and this electronic defect. These are the point defect categories. So next will we move forward for the line defects. So line defects are one dimensional defect and also called as dislocation. So dislocation is basically two types. One is the edge dislocation and the screws dislocation. So edge dislocation, basically in a perfect crystal, atoms are arranged in both vertical and horizontal planes. The atoms are in a perfect equilibrium in their positions, and all both bond lengths are in equilibrium state. If one of the vertical plane does not extend to the full length but abruptly terminates somewhere in between within the vertical in the crystal, then it may be viewed as a half plane constitutional linear defect. Within the region around the edge, there are some localized distortion. It may be seen. Uh, it may be seen from the atom above the edge are squeezed and in the state of compressed, while atoms below the edge are pulled apart or in a state of tension. The region of distortion spread a few lattice distance around the edge. This distortion is known as edge distortion. So in short, we can say that if one of the vertical plane does not extend to full length but abruptly terminate in between, the edge of such plane constitutes a linear defect. The local distortion at the region around the edge, this distortion is known as edge dislocation. Edge dislocation can be the positive or negative. So in this diagram, that an edge dislocation is said to be a positive when the half of plane appear have been inserted from the top of the crystal, and it is uh, denoted by like that sign. And if in an edge dislocation is called as negative if extra half plane lies lower part of the crystals, then you can define as this mark like a T. Now coming to the screw dislocation. The screw dislocation is also called as the Berger dislocation. So here we can see that in this crystal plane we can see that one part is bit down from the other, means bit lower than this part. So here we can see this defined as the screw dislocation. So let us consider here a perfect plane phi, and then the crystal on the right side of the card be shifted relative to that on the left side has occurred by an amount of b, this part. So from the figure it can see that the shift has occurred from the length of atomic spacing in the predominated part of the crystal and reached the line this O dash, this line. So away from this line, the is crystal structure is undisturbed and shows the order atomic arrangement near line O dash, atoms of atomic plane lying on left side and right of the shear plane P have undergone displacement with respect to each other. The displacement cause a local distortion called as a screw dislocation. So here this O dash it's kind of a line of dislocation. So now will we discuss the another type of that dislocation. The Varger vectors is B. A dislocation are quantitatively described by the Varger's vector denoted by V. So Varger's circuit in perfect crystal and in crystal with edge dislocation is edge dislocation. So this is in a perfect crystal, and in the crystal with the screw dislocation you can see here. But you see this is the Varga dislocation in this region. So dislocation qualitatively described by the Barger vectors denoted by B. It tells us the direction and the magnitude of the lattice distortion associated with a dislocation in a crystal. It also describes the sleeve which one part of the crystal undergoes relative to the rest of the crystal. The nature of this dislocation defines relative orientation of dislocation line and the Varcher vector. This vector of an edge dislocation is perpendicular to the dislocation line and that of screw dislocation parallel to the dislocation line. Now coming to the another type of defects, that is the planar defect, or we can say as two-dimensional defect. So in this section we will be discussing on planar defect. So since planar defect is a two-dimensional defect that separates two regions in a crystal. So here it is saying that atomic arrangement at grain boundaries. These defects are the external surface, grain boundaries, tilt boundaries, twin boundaries, and stacking fault. So the external surfaces, the surface of a crystal itself is a defect. The surface atom have formed bonds with neighbors only one side, whereas the atoms inside the crystal formed bonds with neighbor with either sides. Means let's consider that it from this side and this side, from either side it have the bond with the other side. Since the surface atom are not bonded to the maximum number of nearest neighbors, they are in a higher energy state that atoms in the interior of the crystals. So now coming to the grain boundaries, the most important defect in the crystals in crystalline sample is the grain boundaries. So it is one of the most important defect in crystalline sample. A grain boundary is general planar defect that separates region of different crystalline orientation, that is grains within a polycrystalline solid. So now the tilt boundary. So tilt boundary generally formed for the array of edge dislocation. Tilt boundary is another type of this planar defect where the neighboring crystal regions are tilted with respect to another by only a small angle. So you can see that in this here that this side compared to this and this area, you can see that it just bit a tilt by a small angle. Twin boundaries. So a twin boundaries is a special type of grain boundary. Atoms of one side of a twin boundary are located in minor image positions atoms on the other side. So the boundary between the twin crystals will be a single plane of atoms. So we can see that here this is the perfect region and this twin or distorted region is it can be seen in this way. Now coming to the stacking fault. So let us consider a FCC crystals is regarded as formed by stacking of hexagonal closed pack atoms array A, B and C. The sequence will be as follows, like ABC, 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 ABC. If one of the layer go missing, the stacking default occur in the crystal. So if one of the layer here go missing, then we can see this kind of defect. For example, if a layer in the third set of the sequence fails to appear, the sequence change to like ABC, ABC, BCA. So third one is changing here. So then the sequence is interrupted and the stacking fault is produced. So that this are usually produced during the growth of the crystals. Stacking is observed in FCC metals, and now we will be discussing on the volume defect. So volume defects such as cracks may arise in the crystal during mainly the process of the crystal growth. So a crack may result during the growth during possible small electrostatic dissimilarity between the different stacking layer. A large vacancy may arise due to missing of the cluster of atoms is called in the volume defect. So in inclusion of foreign atoms or non-crystalline region of size roughly around 20 angstrom also belongs to this category of the volume defect. So this volume defect is basically the normal three-dimensional defect we can mention as a volume consideration. So now we will wrap up the lectures with highlighting the application of the defects, that how defects are desirable for the crystal and how improve the crystal properties. So all crystalline materials have contain the defects in some form or other. The nature and the effect of such defect are very important in understanding the properties of materials. So first coming to the electrical properties, that when a pure semiconductor is doped with a pentavalent or trivalent impurity, is result in extrinsic semiconductor. So in such semiconductor, the electrical conductivity increases with such doping concentration. In case of metal, the presence of impurity decreases electrical conductivity. So these are the important features of defect in their change of the electrical properties. So now coming to the optical properties, basically the presence of impurity atoms in the crystal results in characteristics colors to the crystals. So basically the optical property changes, and it is very desirable that with the doping, changing the doping percentage, creating such materials for getting different kind of LED lights, different solar cells materials, these are called, and this the materials which are using for changing their colors to the characteristics colors to the crystals are generally called as color centers. When aluminum oxide is doped with the chromium atoms, we get ruby, which is very active laser medium. And another properties I like to add here, the mechanical properties. The plastic deformation is mainly due to the motion of edge dislocation, and the mobility, it affects in mobility of the dislocation. The mechanical strength may be enhanced. So in the mechanical strength enhancement, this can be used, and the restrictions restricting or hindering dislocation motions renders a material harder or stronger. So let's example like copper added to the gold to increase the ductility of the gold, so that uh, it can be drawn into the wires. So in our next we'll focus on, so we'll be show that in X-ray diffraction how we can see this this X-ray diffraction, and how can we find out the interatomic distance and of the crystals, and how we can find out these properties with using. So X-ray diffraction is electromagnetic radiation with wavelength between roughly 0.1 angstrom to 100 angstrom. So it important tool in crystallography is used to identifying phase, quantifying change in the cell parameters. So in upcoming lectures I will be focus on the this defect that influence of the defect, how we can see that cell parameter, orientation, crystal size, and other structural parameter affecting. So this will be focus on upcoming lectures. And thank you very much uh, for listening. Thank you very much.